So anyone who can't be here for the live session will be able to chime in later. I just wanted to touch base because it's been a while since we've met up. And so I want to touch base. I want to go over some NMR stuff that feedback from some previous reports. I am slowly getting caught up with grading. I have some things to review in Gradescope, and I'll post those grades. So 1,000 apologies for lab grading. For 23 years, lab grading always ends up getting pushed behind because it's I think it's that weekly nature. It makes you kind of put it aside. But then, of course, getting ready for writing all new labs, getting those all ready this semester, and then in my lecture class, I've had the pleasure of dealing with some cheating students, and so that sucks down an additional 20 hours that I don't have. So anyway, excuses aside, I do apologize for any backlog there is of grading. And most importantly, I want to make sure that you're getting feedback when it comes to like working on NMR problems. I want to make sure that you have that graded feedback so that you're not making the same mistake, again and again. That should never be happening without a chance to correct. So anyway, please reach out anytime if you have questions about my grading or feedback or anything like that. And I also apologize for my 12 to 2 office hours. I ended up having scheduled appointments all throughout. So if you do have questions about today's lab report is the nylon lab report is due. So if you have any questions about that after we kind of finish up all the stuff I wanted to talk about today, I'll stop the recording and we'll just turn the rest of the period into office hours, and I'll stick around as long as well, I think I have some more appointments coming up, but I'll stick around as long as I possibly can. And then the way I'm doing my office hours right now is I have a waiting room so that I can have confidential meetings. And so if you jump into my office hours and you see, if you're in the waiting room and I don't respond, that means I have a student in with me. But anyway, we'll get through this. And as usual, if the lab report is due tonight, but if you turn it in tomorrow, it's fine. So if you still have questions that didn't get answered today and you still want to follow up with me, I'm very happy to discuss. So that hopefully should work for everybody. So first of all, I wanted to introduce you to the lab we're starting today, which is, can everyone see my screen? I have my screen shared. It's the addition to dienes, and right off the bat, the experiment that we're going to be doing in Beyond Labs is adding HCl to a diene, but it's described as bromination instead of chlorination. So right off the bat, there's like, what? So when you read through the instructions, you'll see that the person who created the handout did a nice job of pointing that out. But what I wanted to talk about was this reaction that we're doing, because this is kind of an interesting reaction that if you're taking 3150 right now, this is a topic that we haven't gotten to yet. We're going to talk about it shortly. And actually, we're talking about this kind of towards the very end of the semester. So we'll get to it eventually. And for those of you who took 3150 already, I spoke to some students today, and I realized that doesn't like make you an organic chemist and make you automatically remember every single reaction you've ever seen in organic chemistry, because some of you it's been quite a while. So I just wanted to review it for some of you and introduce it to others, and that way you'll have some idea of what's going on. So the reaction that we're studying is this: when you have a diene and you add just one equivalent, so that's not explicitly stated here, but if you add just one equivalent of HCl, it's possible to react just a single pi bond with that HCl. But when you do that, you actually end up adding HCl across the pi bond like you might normally expect, right? We would describe that as Markovnikov regiochemistry. Remember that? We haven't talked about that for a while, but the carbon with more hydrogens gets the hydrogen. So that's not too surprising. But we get a second product where the double bond is in between the middle two carbons, and the hydrogen and chlorine are added to both ends. And so we describe those products as the 1,2 product and the 1,4 product. And what's very interesting about them is that one is described as a kinetic product and one is described as the thermodynamic product. And so in Beyond Labs, you explore the reaction, the same reaction, but at different temperatures. And you see that actually lower temperatures favors one and higher temperatures favors another. And so this is just a really significant concept in organic chemistry, that this is a great illustration of that. We will talk about it at great length when we get to this topic in 3150. But I just wanted to touch on it today to give you a little more experience with it. How does the mechanism work? So this is the complete handout, so you can take your time reading through this. But in general, what we're looking at for the mechanism is, as usual, we're going to protonate the pi bond with HBr or HCl, whatever strong acid we have. And again, we're going to do that with Markovnikov addition, because notice the carbon with more hydrogens on the double bond is where we added the hydrogen. And why do we do that? Because that gives a carbocation that is more stable, more substituted. And not only is this a secondary carbocation versus potentially a primary carbocation, but this carbocation is resonance stabilized. So that is huge, because that means that's a very stable carbocation. The other impact of that resonance stabilization is, remember what resonance means, right? It means we have a hybrid. The actual carbocation is some, blend of these distinct resonance forms we could draw. But what we observe is that this carbon, oh, that's too thick of a pen, sorry. This carbon has carbocation character, and this carbon also has carbocation character, right? The positive charge is delocalized in this case over two different carbons, which means in our second step where bromide attacks, right? This is now a nucleophile that it can add to the carbocation. When it attacks, there's actually two carbons that have carbocationic character that are electrophilic, and it could attack to either one. So if it attacks at this position, that's how we get our 1,2 product. The carbon, the bromine and the hydrogen have added right next to each other. And if it attacks this carbon, that's how we get the 1,4 product. So it's the possibility for getting two products arises from the fact that our carbocation intermediate is allylic and therefore resonance stabilized. So hopefully that mechanism looks reasonable to you and you can kind of understand where they come from. But then the additional thing that gets interesting is this idea of being able to control the product distribution based on your reaction conditions. And that's getting into the kinetic versus the thermodynamic. So there's a little discussion of it here in the handout, and you could read through that. There's more of a discussion in Klein. I think that because this refers to Bruce, I haven't, I could maybe send you the link for Klein in chapter 16. If you'd like to learn more about it. But I thought because we've been doing enolate chemistry, I thought I would illustrate this idea of kinetic versus thermodynamic again in terms of enolate formation. And so when you have an enolate and you treat it with a strong base, okay, we have two different, in this case, we have two different alpha protons that we can deprotonate. Right? So let's say our base comes and grabs this proton, for example, that would give me this enolate. But I can also attack the other hydrogen, the alpha proton, and I could get this enolate. So here's another example where a reaction can follow two different paths, right? There's two options out there. And this happens to be another example where one of those paths is described as the kinetic and one is the thermodynamic. So this top one on the top right here is the kinetic, is described as the kinetic enolate. And the other one is described as the thermodynamic enolate. And it turns out we can control which one is formed based on our reaction conditions. It does often lead to conditions where these are done in warm temperatures for the thermodynamic, and cold temperatures are what we have for the kinetic. So the same temperature correlation we see in the Beyond Labs experiment is the correlation that's more generally observed. And we actually just talked about this yesterday, if you were in the problem solving session, that when we use LDA, for example, LDA at minus 78 is one way that you could form this kinetic enolate, and it ends up being governed by sterics, because this hydrogen is on a primary carbon, this hydrogen is on a secondary carbon. This proton is simply easier to grab. It's faster. It's faster. So this is the faster. This is formed faster. And so it has to do with, why is this the faster reaction? Because the lower in sterics, it ends up making it a more stable transition state. A more stable transition state. And that's always going to be true for what we describe as the kinetic product is formed faster, because of lower energy transition state. And so if we do this in a cold reaction conditions, whatever's formed faster ends up being our major product. Okay, now you might think like, well, that's a weird temperature. What the heck? Why minus 78 degrees? That seems very specific, right? Does anyone know where that number comes from? Has anyone done any research in the lab or seen that number before? Minus 78 degrees. That is actually the temperature. So what if I said that this was done at I'm sorry, not minus. What if I said this was done at 0 degrees C? That doesn't seem like a very arbitrary number, right? If I said, I want you to run this reaction at 0 degrees C, how would you achieve that in the lab? Do you have to like get a refrigerator and, a chilling station or something and measure it at 0 degrees C? What's a very easy way to get that temperature? Anyone want to chime in? Ice bath, very nice. So yeah, if the freezing temperature, the freezing point, melting point of water is 0. So just ice water. If you mix ice with water, you are guaranteed to have a 0 degree temperature bath. As long as you still have ice present and you still have water present, you're always going to be in that equilibrium of water freezing or melting, right? So 0 degrees is very easy to achieve. Turns out minus 78 degrees is also very easy to achieve. We just use a special kind of ice. We use dry ice. Now you can't put dry ice in water. You can put dry ice in water. I take that back. And it will cool the water, but you can only cool water so far, right? Once that water gets to 0 degrees, it's going to freeze. You can't cool water below 0 degrees and still have it be liquid. And it's important for a bath, in order to properly cool a flask that you're putting in it, you need to have a liquid. It needs to have that contact with with that you get when you have something submerged in a liquid, right? If you ever try sticking your hand in a bucket of ice, right? Not so bad. Okay, you can kind of handle it. How about sticking your hand in a bucket of ice water? Big difference, right? I mean, they're both 0 degrees, but the huge difference is the water will now have complete contact with your entire surface area of your hand, and be able to conduct the heat away and really transfer that heat and really efficiently cool your hand. So every time we say, hey, put this in an ice bath, what we mean is an ice water bath. So we're going to use dry ice, which is way colder than wet ice, but you can't use water. The solvent we use is acetone. So when you mix, an acetone is a very, very low freezing point. So when you mix dry ice and acetone, it's kind of cool because it bubbles a little, because as the dry ice warms up, it of course sublimes to carbon dioxide. Dry ice means solid CO2. Solid CO2. So we put dry ice and acetone, and if you stick a thermometer in there, you'll see there it is, minus 78. So that is the temperature achieved with the dry ice acetone bath. All right. Sorry, just a little side note there, because that does seem like such a weird temperature if you don't know how to get there. So this is the product that's formed faster because it has the lower energy transition state. This now, if we do under warm conditions with a different base, typically what's going to be happening is we allow this reaction to equilibrate. That's when we get these thermodynamic situations, and that's what the warmer temperature allows. And so the product that results in a thermodynamic situation is not just what's formed faster, It's whatever product is more stable. So the thermodynamic product is the one that is more stable, which means if you let things equilibrate, if it goes back and forth and back and forth and back and forth, eventually you're going to have, we describe it as the thermodynamic sink. We end up always with the most stable product possible, the most stable product possible. So looking at these two enolates, is there something about those two enolate structures that you would actually use to conclude that in fact this second one is the more stable enolate? Does anyone see a difference between those two? They're both resonance stabilized. They both can put the negative charge on an oxygen atom or a carbon atom. Do you see a difference? Do you know anything about alkene stability? Do you know anything about alkene stability? What makes one alkene, one double bond more stable than a different double bond? Number of alkyl substituents. They both have resonance. That's definitely good to look for. They both have resonance. They both have charges on the same atoms. But let's focus on the double bond. This double bond versus this double bond. Do you know anything about alkene stability? What makes one alkene more stable than the other? How about like a mono-substituted versus di-substituted, tri-substituted, tetra-substituted? Do you remember that discussion about alkene stability? When we look at Zaitsev's rule versus Hoffman rule, right? What did we look at? We looked at how many carbon groups are attached, right? So the more carbon groups you have on the double bond, the more stable that double bond is. So this top alkene has just one carbon group attached, but the bottom alkene has two carbon groups attached. So that is, in fact, the more stable place for that double bond to be. And that's why it is, in fact, the more stable product. So if you do this reaction with warmer conditions, you would get this as your enolate. Does that make sense? Any questions about this? So we'll look at this again, at this kinetic versus thermodynamic later in the semester, because we're actually going to study this reaction of 1,2 versus 1,4 addition of HCl or HBr to a conjugated diene. We're going to study conjugated diene reactions after we kind of wrap up stuff with aromaticity. All right, very nice. So just thank you for that brief exposure, you know, moving into that topic of kinetic versus thermodynamic. Okay, so looking at the rest of the lab, there's instructions on what to do at the low temperature and the high temperature. And then the usual, now again, there's no procedure to follow or notebook to do, so we're not giving you amounts and moles and calculations and all that kind of stuff for this lab. So this is asking you just to gather some general information from, you know, an SDS and so on. So do your work, do your research there. And then asking you, we're going to be studying C13 NMR as a way to distinguish between the different products. So reporting the C13 data, assigning the peaks as best you can. You might not be able to assign everything perfectly. And then reporting the temperatures that you recorded in the experiment. And actually, so we're going to be using some different lab equipment in the Beyond Labs. We're actually doing a distillation, which is kind of cool because we haven't done that yet. And we are going to be doing a distillation later in the semester when we isolate eugenol from cloves. So it's nice to think about the distillation process too. So as a way of purification. So lab report questions are here. Someone actually told me that the lab report that's due today, it was prompting for 4 pages, and that's because I kind of had a cover page in the PDF that I uploaded. So I swapped the PDF. Hopefully that worked. And so hopefully when you go to upload it, it should only need I think it was a 3-page lab report. So same thing here. You'll also find online on our course homepage, I have the link for this week's NMR homework, and so it's the usual, you know, with the IR and the proton NMR. So we're going to do our usual work of finding the pieces and putting them together and so on. But you'll notice that I've now added a new feature there's some little data here for the mass spec. In fact, this is the mass spectrum data. So instead of looking at the mass spectrum, you could just report the data here saying that, you know, there's a mass to charge at 31 and that has an abundance of 14, right? So, so it's showing you the relative abundance, that's the height of the peaks, and it's showing you the mass to charge here. So the data is there. And I've just asked you for 3 things, the base peak and 71 and 115. So I'm asking for the mechanism of the formation. So using, you know, the curved arrows to show what bond is breaking and how does it go, how does it break. That's what I'm looking for there, not just the structure. All right, questions about anything about what we're doing in the coming week? Number 1 in pre-lab, number 1 in today's pre-lab.
Yeah, I was just about like
This one?
would recrystallization be suitable? Yeah. Like
Yes.
how would we know that? Because isn't it like, doesn't it remain a liquid after it boils off, like after you boil off the water?
So that this is a question of when do you use recrystallization versus when do you use distillation? So that's what that question is getting at.
Oh, okay.
That's all it is.
I understand now.
Yep, very good. Very good. Any other questions? Any other questions? And like I said, if you have questions about the nylon lab, just hang out and we'll get to those in just a minute. I just wanted to point out a couple things that have come up in my discussions with some of you during office hours and so on. I just wanted to point out some things now that we have a little more experience with NMR. So, so for example, when we look at this this NMR, I see the carboxylic acid here. That's my OH. And I see this big ugly, that's kind of what carboxylic acid, CO2H, OH, it's a carboxylic acid OH. It just ends up being a huge mess. They're really, really ugly IR spectra. But what I wanted to talk about were the aromatic protons. The aromatic protons, because in this case, where are they? They are, as usual, somewhere around 7. But one of them is at 7 and one of them is at 8. There's a huge difference between the 2 aromatic protons, so I wanted to talk about why that is. Okay, and this has to do with resonance effects. We've seen some examples of this. Again, if you're taking 3150 right now, you're going to be seeing just tons and tons and tons of this in the coming weeks. But it has a real dramatic effect on NMR. And so this carboxylic acid group is described as an electron withdrawing group. And it's called that because it can pull electron density out of the ring, and it does that by resonance. So it pulls electron density out of the ring, which puts a positive charge on that neighboring carbon. We call that the ortho position. Ortho to the carbonyl group, we end up with a positive charge. So so, and of course, and we could do that to this side. We could have moved the pi bonds around, and this one we get the same thing because this is a symmetrical structure. This is a symmetrical structure, and everything that happens to one of those orthoprotons happens to the other. So this carbon is really partially positive. Is significantly partially positive. Okay, and it just so happens on the other side we have an oxygen group, which we will see can be described as the opposite, an EDG. This is an electron donating group, and we call it that because with its lone pairs, it can do allylic lone pair resonance, where lone pair becomes a pi bond becomes a lone pair. And what does that resonance form look like? We have now a negative charge next to the OR substituent, the propoxy substituent. So this carbon is hugely partially negative. So remember, it's electron density that tells us whether you have something that's upfield or downfield, what your ppm number is, your chemical shift. It's how electron rich or electron deficient that carbon and that hydrogen are. So we have hugely partial negative and hugely partial positive. In this case, we have both. We have something really pushing it upfield and another group that's actually pushing it downfield, and that's why we have this tremendous split of the chemical shifts by a full ppm. So who is B and C? So which is B and C? So if we look at the one that is partially positive, let's focus on that one. Do you think that would be proton B or proton C? What happens when you are electron deficient? Do you get pushed to the left or do you get pushed to the right? Remember, we can kind of imagine this little wedge down here. You get pushed upfield to the right or downfield to the left. When you're partial positive, it is downfield shift, right? Like what happens when you have an oxygen attached? That's very electronegative. What happens? Down to 4, like this carbon right here, whatever proton D is, that's the one attached to the oxygen because it's all the way down at 4. So electron deficient, we describe that as D-shielded, downfield, all those terms relate to something that is electron deficient, so this must be B. So this is proton B. So that these are HB right next to the electron withdrawing group, and because of resonance, the ones that are right next to the electron donating group, this guy is shielded. We call it being shielded when it's electron rich. When it's electron rich, we describe that surge as an upfield push, being pushed upfield. Very nice. Make sense? Make sense? You think you could maybe look for those kinds of things and explain those things? And again, if you are taking 3150 right now, you will be seeing this. You will be seeing both of these a million times over the next month. And so even though it's kind of new for you now, you will be able to pick those out going down the line. So these are some of the kinds of things that maybe we could expect on our lab final is, you know, can you explain why this chemical shift is higher, this chemical shift is lower, something like that, right? I wouldn't be able to ask you what is the chemical shift, right? Because that you would need to have tables and, you know, calculate. And we don't have tables. I mean, there are tables, but I haven't given you tables to calculate aromatic protons, right? For the only table we have says all aromatic protons are at 7.3, right? So 7.3, go for that. HA is the one on the carboxylic or the ones in the ring. So these are both B and C at around 7 are both the ones that are on the ring. On the ring. Oh, I'm sorry. Thank you. I misnumbered this. It's not A and B, it's B and C. So thank you. So A is right here. A is the carboxylic acid proton. And so B is the one that's further downfield, and then C, I went in the wrong direction. C is the one that is further upfield. But these are the two that are aromatic. These are the two that are aromatic because they're around 7. Sorry about that. Thank you. I created some confusion there. So any questions about that? Just wanted to point that out because another place that this resonance popped up was when we looked at the lidocaine reaction. Okay, in the lidocaine reaction, we started with dimethylamine as our starting material. What do you think about that nitrogen on the ring? Do you think that would be an electron donating group or an electron withdrawing group? What kind of resonance do you think we could do for this? Notice that it has a lone pair. So what does the resonance look like? That allylic lone pair is going to add into the ring. Add into the ring. This is an EDG. This is an EDG. So we can draw a negative charge right next to the nitrogen. Okay, but that doesn't do anything for my proton NMR because that carbon actually doesn't have any hydrogens on it. But there's additional resonance. We can continue the resonance to the next. We can do that in red so it stands out a little better. We could continue the resonance, and we can also put negative charge character on the bottom carbon. And there is a hydrogen there. Oops, sorry. Bump. So when we look at the 3 aromatic hydrogens here, 1, 2, 3, right? Which is the one that, well, we could look at we could see our integration here, that A is a 2 hydrogen signal and B is a 1 hydrogen signal. We can use these numbers down here, or we could use the integral trails. So I know which one is A and B. I know that this must be A and this must be B because we have 2 of one and only 1 of the other. But does it make sense why B is the higher? Look at this one is actually, it's a 6. This is at 6.6, an aromatic proton at 6.6. Does it make sense why it's so far upfield? Does that make sense? It is very electron rich. That electron donating group, the nitrogen, is causing that proton that's all the way across the ring. It's para to the substituent all the way across the ring, but still, because of that resonance, this is very electron rich. So that was kind of interesting. Okay, but then after we did the acylation reaction, we reacted with an acid chloride. Look what happened to my aromatic protons. They all coalesced and showed up grouped together all somewhere around 7. So something changed to our resonance. Something happened to our resonance. What happened to the resonance? That lone pair still can add into the ring, okay, but it is not as significant. It's not as great. It's no longer at 6.6. Why is that resonance not so robust? What does the carbonyl do for us? It competes now and pulls that electron density in a different direction. So the amide is doing resonance. The lone pair is doing resonance with the carbonyl. So the amide is, we describe this as a weak electron donating group because it does a little bit of resonance added into the ring, but dramatically reduced compared to the NH2, which is a strong electron donating group. So so now there's no significant difference. We still have these 3 hydrogens here. They're still different, but they all show up together. They all show up as B because there's no significant change in the chemical shift. All 3 protons end up in the same thing. HD in the first spectrum. HD, what protons haven't we labeled yet? What protons haven't we labeled? Look how big HD is. That's a huge signal. So if this is 1, 2, 3, 4, 5, where do we get 6 hydrogens in this for dimethyl Where do we have those 6 hydrogens? You see where they are? We have these 2 methyl groups. We have those 2 methyl groups. So we have they're equivalent. So we get 6 altogether, and they're a singlet because they have no neighbors. They're around 2.2 because they're benzylic. So they're exactly where we want them to be, where we expect them to be, So these are really good exercises, and that's why. So the homeworks are one thing where, hey, here's an NMR, and I want you to come up with the structure, right? I mean, that is a good skill, and that's an important skill. But most of the time in lab, this is what we have. I know what I put in the flask. This is not a mystery. I know what I'm expecting to have made, but I need to be able to confirm this is the structure, this is the NMR. Do they match? Did I actually make what I think I made? So that's kind of like the baseline skill that we should have coming out of lab, that absolutely I can match every single peak in this spectrum with every single peak in this structure and explain why they in fact match, right? So that is one skill that will be tested on the in lab reports and on the lab final. But then the other skill is also, okay, here's the NMR, here's the formula, you come up with the structure. That's where we kind of go through our steps to have a systematic approach to that. All right, fantastic. Okay, one more thing, I think. One more thing, just one last thing, because this is a nice opportunity to talk a little bit more about C13 NMR. And I'll post this handout. I didn't have it ready beforehand, so I'll post this handout to our course homepage. You already have this handout. This talks about C13, right? And how we expect our carbonyls somewhere around 200, and our sp2 carbons, you know, kind of 100 to 150, and then the rest of our sp3s are pretty far further upfield. Okay, but what I wanted to talk about was an interesting experiment we could do called DEPT. So it's called a DEPT C13, and there's a question in the lab report that asks you about it, and so I just want to introduce it to you. And maybe after we have an introduction, maybe we can, you know, I might include it in a future homework set. But for now, I just want to introduce it to you. And so normally when we look at a C13, if we look at this bottom one here, this C13. So normally in a C13, we just get one peak for every carbon. So it kind of tells us like how many unique types of carbons we have, right? By doing a series of experiments called, that are described as DEPT, we run the NMR a second time and then a third time. This one's called DEPT 135. This one's called DEPT 90. And it allows us to start learning more about each peak. And here's what happens. When we do the DEPT 90, all of the NMR signals disappear except for the ones that correspond to CHs. So this is CH only. CH only in the DEPT 90. So you now look at your entire NMR and you say, hey, I see that now I know which ones are the CHs in my structure. Okay, when you run the DEPT 135, you see the CHs and the CH3s, CH and CH3s show up as positive peaks. But then check this out. If you ever have a CH2, it shows up as a negative peak. Okay, now again, don't panic. Again, if I ever test you on this, you will have notes with you. Okay, I just wanted to introduce it as a way of learning that you can in fact make these distinctions and learn on a given C13 for each one. Is it a CH3, CH2, CH, or is it a carbon with 0 hydrogens on it? So how can I tell which one has 0 hydrogens on it? Those are the ones that these two have no hydrogens. Those correspond to the alkynyl carbons, and they don't show up in any of the DEPT experiments. So by using the original spectrum and the DEPT 135 and the DEPT 90, when we compare all three of those together, it lets you identify every single carbon as this is quaternary, this is quaternary, this is a CH, this is a CH, this is a CH, and so on. This is a CH2. You can find out, you could identify each of them. So I just wanted to introduce that concept to you. But we won't go any further than that. That's a really handy advanced technique that you can use that to help answer one of your questions on the lab report. Okay, questions about this one? We'll go through just one quick example. So if we have this structure, okay, I'm giving you the structure. I've numbered the peaks to correspond with each carbon in the structure. Let's see if we could predict what the DEPT 90 and DEPT 135 would look like. The DEPT 90 and the DEPT 135. So for carbon 1, notice that's all the way down here at 200. So that is my carbonyl. Even if I didn't label that, you probably should have been able to pick out that this must be carbon 1. It is a CH. That carbon has 1 hydrogen attached. So does it show up in the DEPT 90? The DEPT 90 is only CHs. So yes, it's going to be in the depth 90? Does it show up in the depth 135? Yes, everything shows up in the 135 except for the quaternary carbons. And the CHs and CH3s are positive peaks, and only the CH2 is the negative. So yes, it's going to show up here as well. How about carbon 2? How about carbon 2? Does this carbon show up? Here's carbon 2. Does that carbon show up in the depth 90? It is a quaternary carbon. It is a quaternary carbon. And what happens to quaternary carbons, like these two? They are absent in all of the depth 135, or the depth 90 and the depth 135. So this is there 2 and 3. I'm sorry, 2. Sorry, I don't want to get ahead of myself. 2 is missing. 2 is missing. How about 3? 3 is a CH2. It has 2 hydrogens on it. So that doesn't show up in the depth 90 because, again, depth 90 is CH only. Depth 90 is CH only. So it shows up in the depth 135. And what happens to the CH2s? The CH2 is the fun one that is the negative peak. So it still shows up at the same ppm. So we align them so you can compare what happened to that peak at all 3 experiments. How about 4? Does it show up in the 90 or the 135? In the 90 or 135? I think it shows up in both because it's a CH. So it shows up in both. Carbon 5. Carbon 5 is a CH2. So it's only in the 135 as a negative peak. And 6 and 7. 6 and 7, they're very, very close. Okay, but the depth experiment is going to single them out because the CH6 is a CH, so it'll show up in both. But the CH3 only shows up in the 135. So that's a way that you can distinguish between 2 very, very close peaks. This one's a CH, this one's a CH2, etc. Okay, so just nice opportunity to explore some advanced NMR techniques. This one is pretty straightforward. It's called DEPT, D-E-P-T. So you can search for that in the Klein text. You can Google it. You could Wikipedia it. You could lots of ways to find out some more information if you want any more information there. All right, questions. I think that's all I wanted to share with you guys in terms of a little mini lecture. Is never missing an opportunity. That is one of the things I really miss is that face-to-face we have, where in the pre-lab lecture you could kind of just bring in these things, but I really didn't want to just make you all sit through a synchronous session if I had just one little tidbit to share with you. So I waited for a bunch of them to kind of build up, and hopefully spent our time together wisely for the time we had. So I will end our recording here. You're free to leave, but you're also free to hang out and ask questions if you have questions. So otherwise, bye-bye. You can email me with any questions down the road.